Welcome to our video presentation on Chapter 13, Solutions. This chapter explores the fundamental concepts behind homogeneous mixtures, covering how they form and how their concentrations are determined. In this video, we will review the learning objectives for this chapter, including calculating mass percent and molarity, using dilution equations, understanding solution stoichiometry, and exploring freezing point depression and boiling point elevation. We will cover sections 13.2 through 13.6, discussing types of solutions like saturated and supersaturated solutions, electrolyte behaviors, gas solubility, concentration calculations, and the dilution equation, M1V1 equals M2V2. Mixtures can be categorized as either homogeneous or heterogeneous. Homogeneous mixtures are referred to as solutions, which consist of a solvent that dissolves one or more solutes. Solutions are classified by particle size. True solutions have the smallest particle size, followed by colloidal solutions, and finally, suspensions, which feature the largest particles. Understanding how to express concentration is key. This table outlines the common ratios used, including percent by mass and volume, molarity, molality, and mole fraction. Solutions come in many forms depending on the phase of the solute and solvent. They can be gaseous, liquid, or solid, with common examples ranging from air to soda water and metal alloys like brass. A tragic example of solution dynamics occurred at Lake Nyos in 1986. Carbon dioxide held in solution at the lake's bottom was suddenly released, leading to lethal consequences for the surrounding area. The incident happened because high pressure allowed dangerous concentrations of CO2 to build up. When the water was disturbed, this pressure dropped, causing the gas to rapidly escape and displace air in the valley. To prevent future disasters, scientists installed a venting system in 2001. This system continuously and safely releases carbon dioxide from the bottom of the lake to keep concentrations at a safe level. This scenario demonstrates that a solution is simply a homogeneous mixture of two or more substances. Solutions are incredibly common, found in everything from the air we breathe to blood plasma. In a solution, the solvent is the majority component, and the solute is the minority. Water is the most common solvent, forming aqueous solutions, while other solvents are used specifically for nonpolar substances. When selecting a solvent, we follow the principle that like dissolves like. Polar solvents are effective at dissolving polar solutes, while nonpolar solvents are used for nonpolar solutes. The formation of a solution occurs when the attractions between the solvent and solute molecules are strong enough to overcome the existing attractions between solute molecules and between solvent molecules. When a solid like sodium chloride dissolves in water, the positive ends of water dipoles are drawn to the negative chloride ions, while the negative ends of water are drawn to the positive sodium ions. This video shows how a solid dissolves in water. When sodium chloride is placed in water, the molecules surround the individual ions, effectively pulling them away from the crystal lattice and dispersing them throughout the solution. Next, we define solubility and saturation. Solubility is the maximum amount of a compound that can dissolve in a specific volume of liquid. A saturated solution holds this maximum amount, while an unsaturated one can still dissolve more solute. Sometimes, a solution can hold more than the normal maximum amount of solute, which is called a supersaturated solution. In such cases, the excess solute will typically precipitate or fall out of the solution. Supersaturated solutions can occur due to sudden changes, such as pressure drops. A notable example is the CO2 saturated water from the depths of Lake Nyos, where changing conditions cause the excess gas to be rapidly released. When considering the solubility of ionic solids, qualitative rules help predict outcomes. For instance, if the attraction between ions in a solid is stronger than the interaction with the solvent, the compound remains insoluble. Molecular solids follow different rules. Polar solids, like table sugar, are generally soluble in water, whereas non-polar substances like lard or shortening are typically insoluble in water. Solutions are also classified by their electrical conductivity. Electrolyte solutions contain dissolved ions and conduct electricity, while non-electrolyte solutions contain dissolved neutral molecules and do not conduct electricity. Temperature plays a significant role in solubility. Generally, as temperature increases, the solubility of solids in water also increases, which is a key concept in many chemical processes. This temperature dependence allows for purification through recrystallization. By creating a saturated solution at a high temperature and cooling it slowly, pure crystals form while impurities remain in the remaining liquid. You can observe recrystallization at home by making rock candy. By cooling a saturated sugar solution, the liquid becomes supersaturated, forcing sugar molecules to crystallize onto a string over several days. Gases also dissolve in liquids, which is how we get the carbonation in soda. Common examples include dissolved oxygen in natural water sources for aquatic life and the various gases present in our own blood. Interestingly, the solubility of gases behaves differently than solids as temperature rises. The solubility of gases actually decreases when the temperature of the water increases. You can see this in a pot of water on the stove. Before boiling, small bubbles of dissolved air form as the water warms, because those gases become less soluble and leave the solution. Henry's law states that gas solubility increases with higher pressure above the liquid. Opening a soda can releases that pressure, which explains why the carbon dioxide immediately escapes, causing the characteristic fizz. Finally, we specify concentration using mass percent, which represents grams of solute per 100 grams of solution. Remember that the denominator must be the total mass of the solution, including both solute and solvent. Mass percent can be used as a conversion factor between the mass of the solute and the total mass of the solution. To do this, simply express the mass percent as a fraction. For example, if you have a water sample that is 8.5% carbon dioxide by mass, you can determine the amount of CO2 in 28.6 liters of solution by using the solution's density to find the total mass. We map out the solution by converting volume to mass using density, and then using the mass percent conversion factor to find the grams of solute required. Environmental chemistry is affected by persistent organic pollutants, or POPs. These harmful chemicals often enter water sources through industrial, agricultural, or household waste. POPs are particularly dangerous because they are fat-soluble. They undergo bioamplification, where they accumulate in fatty tissues and increase in concentration as they move up the food chain. Another way to specify concentration is through molarity, denoted by a capital M. Molarity is defined as the number of moles of solute contained in 1 liter of total solution. To prepare a solution of a specific molarity, you measure the solute, add it to a volumetric flask, and carefully add water until the final desired volume of the solution is reached. Here is an example calculation. To find the molarity of a solution containing 15.5 grams of salt in 1.5 liters, we first convert the mass of the salt into moles using its molar mass. We can also use molarity to perform calculations, such as determining how many grams of a substance are contained in a specific volume of a solution with a known molar concentration. By using the molarity as a conversion factor, we can link the volume of the solution directly to the mass of the solute required for our calculation. When dealing with ionic compounds, the reported concentration represents the state before the compound dissolves. Once in solution, we consider the dissociation of ions. For instance, a 1.5 molar solution of sodium phosphate would result in higher concentrations for the sodium ions compared to the phosphate ions due to the stoichiometry of the compound. Chemists often use stock solutions, which are highly concentrated. To reach the desired lower concentration for lab work, we use the dilution equation, M1V1 equals M2V2. This equation works because the total moles of solute remain constant during the dilution process. Remember, this formula is specifically for dilutions, not for stoichiometry. Finally, safety is paramount. When diluting concentrated acids, always add the acid to the water, not the other way around, to prevent dangerous exothermic reactions.